Naming multivalent cations. Some elements have more than one possible oxidation number. So this results in multiple possible compounds. It's like CO2 and CO. So carbon is in group 14. If you look at the periodic table, you'll see as a cation, it can either be +2 or it can be +4. This causes a problem with naming because normally, using the monatomic rules we talked about before, this would just be carbon oxide. But carbon oxide could be either this one or could be this one. That's that problem we ran into with carbon and with elements having multiple possible valences. We need a way to give it a unique name. That's the rule. Chemical names have to be unique. You cannot have two different compounds like we do here that have the same name. And so you cannot say that those go back and forth to each other. This cannot be carbon oxide because that's an ambiguous name. You have to have an unambiguous, unique name for each compound. So, to distinguish between compounds, we're going to add something to the name of the cation to indicate which oxidation number the cation has. And that's going to depend on whether it's a metal or not for the cation. So, to determine the name of the cation, with two or more possible oxidation numbers, let's first determine if it's a metal or a nonmetal. And so we look at the periodic table. Remember our metal-nonmetal line sort of goes right through here. Elements that are up here are going to be nonmetals. Elements that are on the left and down are going to be metals. Okay? So if the cation is a metal, there are two possible systems we can use. The stock system, sometimes called the IUPAC, after the body of people who basically is sort of in charge of determining standards for chemistry. That's the International Union of Pure and Applied Chemistry that sort of approved this system. So the stock or IUPAC system, this is the one you're going to use most of the time. The other possibility is you could use what's called the old or the classic system. This is an older system that goes back a little farther in time, not as new, it's not as flexible, and it's harder to use. And so if you have a choice, typically pick the stock system. That's going to be the one you're going to want to choose. But you do need to know how to figure out the formula with things named using the older classic system. So we're going to look at both of them here. But these two systems work if the cation is a metal. If it's a nonmetal, there's a third system we'll talk about in just a little bit. So, in the stock system, the rule is that a Roman numeral is placed in parentheses after the metal name to specify the valence. So, let's take iron, Fe. If you look on the periodic table, it's not in one of those groups that we discussed, not one of the columns that fits one of the rules. We look at the periodic table, it's there in group 8. It says that iron has two possibilities. It's either +2 or it's +3. And so because there are two possibilities for it, it is multivalent. There are more than one possible valence for it, more than one possible oxidation number. And so we have to specify which one. And so if this were iron 3, then we'd write it as iron parentheses III, because that's Roman numeral 3, close parentheses. Okay? A couple things notice. Roman numeral have to be all capitalized. Okay? Now, number 2, notice this is not a typo. There is no space between the name and the opening parenthesis. Okay? You write iron, no space, open parentheses, 3, Roman numerals, close parentheses, and that's it. All right, so that's how you'd write that out. If this weren't iron 3, if instead this were the other valence, so this one right here is this guy right here, but if it were this one, then we'd write it out as IRON, open parentheses, Roman numeral 2, like that. So that would be iron 2, and then this would be iron 3. Other examples we'd have, manganese 7. Looking at the periodic table, manganese has possible valences of +2, +3, +4, and +7. So which one is it? We show which one it is by writing in parentheses, manganese 7. This number right here is the oxidation number or the valence, okay? And so that's what we have there. Gold is another one that's multivalent. And so gold, if you look at the periodic table, it's not one of our common rules. It's +1 or +3. In this case, it's +1, okay? If we're doing silver, silver is Ag. And we're trying to figure that out. We look at the periodic table. Silver has a valence of just +1. And so if we were writing it out, we would just write silver. We don't have to put a number in parentheses after it because there's only one possible valence, just +1. But if it's multivalent, silver's monovalent. If it's multivalent, then we do have to put it in parentheses if we're using the stock system. So in the stock system, let's take this compound, Ir2O3. It would be iridium 3 oxide. So the way we know it's going to be iridium 3 oxide, and I'll delete this part out right here just so we can do the math on it, is that iridium, looking at the periodic table, could be either +3 or +4. So two possibilities, +3 or +4. Oxygen, on the other hand, is over there. It's one of those with that special rule, and it's in column 16. It's going to be -2. And so since there are 3 oxygens, so 3 -2s gives us a total of -6. To make the total compound be 0, that means the iridiums have to add up to +6. Since there are 2 iridiums, it's 2 times what is 6? Well, 2 times 3 is 6. So that means this is the valence of the iridium in this compound. And so that's why we say iridium-3 oxide like that. Now our other possibility is, what if this were iridium-4? So if it's iridium-4, then that would mean there's 1 iridium here, it's +4. There are 2 oxygens, so 2 times -2 for the valence of oxygen, so that gives you -4, so it balances out. So IrO2 is iridium-4 oxide. So you can see that if we just said iridium oxide, you wouldn't know whether it's this guy or this guy. There'd be no way to tell. But by, say, iridium-3 oxide, you're able to say, oh, that 3 tells me this iridium is a +3 ion right here. If it says iridium-4, that tells me this iridium is a +4 ion. And then that'll force this to be 2 oxygens right here, or the iridium-3 would force this to be 3 oxygens to balance out those oxidation numbers, to balance out those valences so that it would work out. So that's how the stock system works. Stock system can be used for any multivalent metal cation, no exceptions. Other system we can use is the old system or the classic system. Old system can be used if there are only 2 possible positive oxidation numbers for a metal cation. So when we ran into manganese before, manganese we said was +2, +3, +4, +7, we could not use the old system because it only works if there are 2. Because we're going to see it requires that we look at the larger or the smaller of 2 things. It's comparative. It doesn't work if you have more than 2. It's one of the reasons why they had to develop the stock system later on. So, in the old system, the ending of the metal name is dropped and replaced by IC if the metal has the larger of the 2 valences, or replaced with OUS if the metal has the smaller of the 2 valences. So using this old system, we said IR2O3. Remember, that's the one that we said had to be the iridium-3, and then the IRO2 was the iridium +4 right here. So iridium-3 compared to the iridium-4, 3 is the smaller one. And so we would take the word iridium, IRIDIUM, drop the ending IUM, add the ending OUS because the +3 is the smaller of the 2 between +3 and +4, and if it's the metal is the smaller one, it's going to be OUS. And so it becomes iridous oxide would be our compound name for IR2O3. But IRO2, because it's the +4, the larger of the 2 valences, then we drop the IUM off iridium and add IC because it's the larger of the 2, and so it becomes iridic oxide. And so that's what you do. And so if we were looking at, let's say, nickel, nickel is either +2 or +3. If it were nickel-2 oxide, it would be nickelus oxide because OUS shows you it's the +2, it's the smaller of the 2. If it were nickel-3 oxide, in the stock system, it would be nickelic oxide. And so that's how that works for old system. One thing to watch out with the old system, added complexity, is that if the atomic symbol does not match the English name of the element, like for example gold, symbol for gold is AU. How does that make sense? You'd think it'd be like GO or G or something, but the reason why is because this is one of the ancient metals. It's been known for thousands of years, and so long before there was an English language, and so these were originally named using other languages, specifically Latin, the language of the Roman Empire, and so because the symbol doesn't match up with the English name, the old system name isn't going to match up with the English name either. And so we have to use the Latin root of the element name. And there are only a few of these that work like this. And so iron, the symbol is Fe. The Latin word is ferrum. And so when using the old system, if it's the larger oxidation state or the larger oxidation number for iron, then it's ferric. So if it's iron is +2 or +3. And so if it's iron +3, then it would be ferric oxide or fluoride or whatever it is. If it was iron plus 2, it would be ferrous right here. Same thing is true for copper. Copper, symbol Cu, there's no U in copper. That's because the Latin word, it's taking the Latin word cuprum, and so it's cupric or cuprous. Tin is Sn, that comes from the Latin stannum, and so that stannum right there goes to stannic or stannus. Gold, Au, is aurum in Latin becomes auric or aurus using the old system. Lead, Pb, plumbum, for the root we get the word plumber from because the pipes used to be made of lead, is either plumbic or plumbus. Now, one that looks like it should fit this rule but actually doesn't, and I don't know why, is mercury. Mercury in English, named after the planet, is Hg. The Latin word is hydrogyrum, and so, but nevertheless, it's not hydrogyric or hydrogyrus, it's actually just mercuric or mercurus. The other one that's like that, I forgot to put that on here, is antimony. Antimony is Sb, but it's still antimonic or antimonous, I'm pretty certain, on those two. So that's something to watch out for whenever you're naming these. Nonmetals. If the cation is multivalent and a nonmetal, like for example, looking at the periodic table, nitrogen's the classic one right here. Nitrogen as a cation has many, many possible valences, +1, +2, +3, +4, +5, in addition to the -3 that's most common with nitrogen. It's normally, because it's a nonmetal, going to be an anion, but if it's a cation, it could be one of many, many possibilities. And so what we have to do is we have to indicate which oxidation number indirectly. We don't say it like with the metals where we say it straight, nitrogen 4, or something it's like nitrous or nitric. We don't do that whenever we have nitrogen or other nonmetals, the cation. Instead, what we're going to do is we're going to use a system called a numerical prefix system to describe the number of each element's atoms in the molecule. And so in this numerical prefix system, we add a prefix to the anion name indicating how many anion atoms are in the compound's formula. And so if we had an O2 right here, normally if this were not multivalent, it's just to be nitrogen oxide. We're going to add a prefix in front of the oxide that tells us how many oxygens, in this case 2 oxygens. So we would say nitrogen dioxide for this right here. That would be our first step. If doing that makes the name completely unique, it can only describe NO2 and that's it, then we're done. It'll just be nitrogen dioxide. But if the name is still ambiguous, once you've done that, then you're going to have to add a prefix to the cation as well. And so if this one right here were unambiguous, we haven't checked it, but if it were, ambiguous, if it could be that nitrogen dioxide could be more than one thing, then we'd also have to say, how many nitrogens are there? There's 1. And so that implied 1 that's right here. So we'd say it would be mononitrogen dioxide to specify which one it is. So let's look a little bit more at this one. So let's take SO2. And so SO2, the name cannot be simply sulfur oxide because if we look at the periodic table, we can see that sulfur is normally, it's in group 16, which would normally give it a -2. But because it's with oxygen, we said oxygen had that higher rule on that, so oxygen's got to be -2, which means sulfur has to be the cation. Other way we know it's the cation is because it's first. Remember, it's always cation first and anion. So we know the sulfur is positive something. So we look at the periodic table to find its sort of non-standard one, and it tells us that sulfur could either be +4 or +6. So it's either +4 or +6. So if we just said sulfur oxide, we would have no idea whether it's sulfur 4 or sulfur 6. We're going to have to say which one it is. Sulfur is multivalent. So sulfur is a nonmetal, so we're going to have to use the numerical prefix system. So we're starting off with sulfur, and we have oxide. I'll put a little space because I think we know we're going to have to add something in front here. So we say, using the numerical prefix system, we say how many oxygens are there? There are 2, and so over here we can see 2 gives us the prefix of di. So this would be sulfur dioxide as long as that's not unambiguous. Okay, now in this case, this would give us a valence of sulfur 4 because if I have 2 -2s, that's a total of -4. There's only 1 sulfur, -4, 4. There's only 1 sulfur, which means that has to be +4. Okay? What if the sulfur were +6? What would we name it then? Well, if the sulfur was +6, I'd have to have 3 oxygens, and so my formula would be SO3, and that should be a little subscript 3 down there. So that would be SO3, and so this would be sulfur trioxide because there are 3 oxygens, the numeral 3 goes to tri. And then we have the rest of the list going down here from 1 being mono all the way out to deca being 10 right there. Let's take a look at another one. Case where prefixes are needed on both cation and anion would be this right here, S2O6. So sulfur, as we saw before, is multivalent, either +4 or +6. So you'd say, okay, I got sulfur, I got oxide right here. You'd say, okay, since sulfur is multivalent, I got to describe the number of oxygens. It's 6. 6 is hexa. So I would do hexoxide right here. So sulfur hexoxide. Am I done? Well, you normally would think you would be, let's check and see if this answer, this name, is ambiguous or not, or is it unique? Could it only be S2O6? Well, the other possibility, there is another possibility this could work at, because if I had 6 oxygens, oxygen is -2 for its oxidation number. That gives me a total of -12. Well, the two possibilities for sulfur were +4 and +6. So this one right here, this S2O6, there are 2 sulfurs, so 2 times 4, is that 12? No, 2 times 6 is 12 though. So this is the sulfur +6. But what if it was sulfur +4? Well, 6 goes into 12, but 4 goes into 12 as well. So I could have S3O6. This would work fine because if this were sulfur +4, +4 3 times is +12. Oxygen is -2. 6 times -2 is -12, so that works. So sulfur hexoxide has 2 possibilities. That could be S2O6 or it could be S3O6. And so this name is not unique. We're going to have to add something in front of the sulfur right here so that we end up with a unique name. And so to do that, we're trying to name this guy. We'd say, well, what's the prefix on sulfur? Well, there are 2 sulfurs. Prefix is di. So we'd say it would be disulfur hexoxide would be the name of this guy right here. Whereas this one, the S3O6, we'd have to add a 3. That's going to be tri. So it would end up being trisulfur. I think oops, that should be trisulfur down here. I said di. It should be trisulfur hexoxide would be this one because of the fact there are 3 sulfurs that are right here. One last note with numeric prefix system, just a naming one here. If numeric prefix ends in an A, so you can see tetra, penta, hexa, hepta, octa, nona, deca right here, if it's one of those, and the non-metal name begins with the letter O, which is oxygen, then the A is dropped. And so you actually may have noticed this a little bit with this. We didn't say hexa oxide, we said hex oxide. That was because of the fact that hexa ends in A, oxygen begins in O, and so it becomes hexoxide. If you had 5, it wouldn't be pentaoxide, it would just be pentoxide. And so that's something to look into. Looking at a couple of examples. So the 2 that we have, one of which is N8O4. And so for N8O4, we first say, all right, so our cation here is going to be the nitrogen right here, the anion's the oxygen. So is the cation multivalent? So we look at nitrogen and we said, oh yes, +1, +2, +3, +4, +5. We don't know which one it is, but it's definitely multivalent. So is nitrogen a metal or non-metal? It's definitely a non-metal. It's it's on the right and toward the top, and we know nitrogen is a gas, it's not a metal. So it's a non-metal, we're going to have to use our prefix system. So it'll be nitrogen, and then oxide, but there's going to be a prefix in front of at least the oxide, maybe in front of the nitrogen too. So if the prefix is in front of the oxide, we look at 4. Well, the prefix for 4 is tetra, like you know the game Tetris, because each piece is made of 4 blocks. So it does end in A, and this begins in O, so it'll just become tetroxide, T-E-T-R-O-X-I-D-E. So nitrogen tetroxide. So this may be the name. We got to check and see if this is ambiguous or not. So oxygen we said is -2. There are 4 of them, gives us a total of -8. That means all the nitrogens have to be +8. And so the question is there only one possible valence or oxidation number for nitrogen that goes into +8? Well, we said nitrogen was +1, +2, +3, +4, and +5. And out of those, is there only one that goes into 8? Nope. 1 goes into 8, 2 goes into 8, 4 goes into 8. So there are 3 possibilities that nitrogen tetroxide could be. So we've got to say which one. In this case, since there's an 8 right here, then we would say octanitrogen tetroxide would be our full name for N8O4. Let's look at our next one, NF2. As we said before, nitrogen is definitely multivalent. It is a non-metal, and so it's going to be nitrogen and then F. So that's our cation is nitrogen, nitrogen, but we're going to need some prefixes here. And then F is fluorine, drop the INE, add IDE, so fluoride, F-L-U-O-R-I-D-E, but we need a prefix. So we've got a 2 out here, so that would be di. So nitrogen difluoride. Question is this ambiguous? Well, fluorine is always -1. There are 2 of them. Total is -2. And so for the nitrogen right here, has to be a total of +2. So looking at our nitrogens, is there only one valence of nitrogen that fits into +2, or is there more than one? There's more than one. +1 would go into +2, +2 would go into +2. None of the other ones were, they're too big. But so there's ambiguity here. It could be nitrogen 1 or nitrogen 2. In this case, it's nitrogen 2 because there's only one of them, so that has to be a +2 right there. And so to show that, I'm going to say there's only one. I just indicate there's one nitrogen here, and so that's going to be mono. So it's mononitrogen difluoride would be the name of this compound.